is Professor Don Yang from Shenzhen Institute for Quantum Science and Engineering, SUSTech. The title is Distributed Private Randomness Distillation. So please.
Okay, good morning, everyone. First, I would like to thank the organizers to invite me here to give a talk. Today, I will talk about distributed private randomness distillation, and this talk is based on the joint work with Karol Hordetsky at University of Gdansk and Andrzej Winter from University Autonoma Barcelona. This is the outline of this talk. In the first part, I will introduce the notion of randomness and say something about the motivation of this work. And the second part is about the main results. And in the last part, I will give a brief summary and some open questions. So randomness, we know that randomness is an important notion that has various applications in science and technology. For example, in quantum information theory, the BB84 protocol use randomness to secure the security of the quantum key distribution. And in the experiment of checking non-locality, we have to use randomness, for example, to verify the violation of Bill inequalities. However, in the classical world, only pseudo-randomness can be generated, for example, by some complex algorithm in a computer. But the randomness, the random bit has been already determined by a hidden variable. So that's why it is called pseudo-randomness. It is not true randomness. But conceptually, it is rather easy to generate true randomness in quantum mechanics. For example, if Alice measures the pulse state in the measure basis 0, 1, then the measurement outcome 0 or 1 is truly random, in the sense that anyone cannot predict what the outcome is in advance. And here, the bit is not only random, but it is also private, in the sense that anyone cannot know the outcome, the measurement outcome, except that after the measurement, Alice declares the outcome. Here, especially the randomness is private to any other adversaries. And the privacy here comes from that a pure state of a quantum system naturally exclude any correlations with other quantum systems. And what about the quantum system, a quantum state correlated with another quantum system? Here it is the eavesdropper's system. And indeed, this is another extreme case. For example, this is the failed state. And if Alice performed the measurement still in the measurement species 01, of course, the measurement outcome is random, but here random is not private in the sense that the measurement outcome 01 is perfectly correlated with Eve's system. And if Eve performed the same measurement, then he can obtain the outcome of Alice measurement outcome. So, so in this state, if we discard the state of E and just look at the state of system A, then it is a maximum mixed state. And in this work, we call this state as local noise because it is maximum mixed. In many protocols, it plays as a rubbish. So, and indeed here, we can see that local noise itself is useless. Indeed, these are two extreme cases to extract randomness. One is pure and the other is maximal correlated with other systems. Then a natural question is to ask, what about a general mixed state? In the sense that Alice system is correlated with adversary system partially, but not completely correlated. And indeed, this work considers such a general case, and here the scenario is rho AE is a generic mixed state. It is correlated state, and now Alice's task is to generate private randomness from this correlated state. And the strategy of Alice is to rotate the state and just to perform a standard measurement or part of the state and keep the other part as a shielding system. And after the measurement, then the outcome is almost decoupled from Eve's system. So, and then the question is to ask, what is the maximum rate to distill private randomness from a given mixed state rho AE? Of course, I should say that here we consider the asymptotic identical independent distributed case. So in this setting, when we consider the maximum rate, and this work gave the answer to this setting, and the rate is given by the log A here. A denotes the dimension of Alice quantum system, and here is a given E is the conditional entropy of the state rho AE. And indeed, when we have know this result, we know that there is a hidden point in the BFW protocol. in the sense that they implicitly assumed trusted by passive Bob. Why? Because here E play as a role of adversary, and definitely because he is adversary, he will not collaborate with Alice to verify the biparty state of rho AE, right? But then Alice herself cannot check the state rho AE, in the sense that he does not know what rho AE look like. So if you assume that Alice knows the form of rho AE, you implicitly assume that there is some way that Alice can check the state is really rho AE. So in their work, they assume that Alice knows the state. That immediately means that Alice has some way to check the state. And the unique way to check that is Alice has a friend, Bob, who holds the purifying system of rho AE, in the sense that no, the tripartite state rho ABE is pure. Then, of course, with the help of Bob, then Alice can check the state rho AE, and then he knows the correlation with Eve. But if there is no such Bob, then in the spirit of being cautious in cryptography, Alice has to assume that Eve holds everything of the purifying of the state rho A. That means rho AE is pure. Then you cannot consider the setting of generic mixed state rho AE. So here we have to introduce Bob. Indeed, in the BFW protocol or in their problem, Bob just plays as a passive role, in the sense that after checking the state or the correlation with Alice, then Bob keeps silence. So, so our motivation from this work is that why not make Bob active? So this is our scenario, and the phi ABE is a pure tripartite state, and now the task is that Alice and Bob, they collaborate with each other to generate independent and independent local private randomness against 2Eve. So this is a distributed randomness extraction that is a dual setting to the well-known Slepin-Wolf problem in classical information theory, where they consider that joint probability distribution, that the data is stored in the probability in distributed region, and the task is to compress their data individually, and then they send their compressed data to a common party such that the common party can recover the original data faithfully. And our setting is almost, in the sense that in the distributed region, they directly extract the randomness. So it's a dual setting to the slapping off problem. So naturally, our task is our goal is to know to determine the region of randomness that can be extracted by Alice and by Bob. That means we have to consider the region AB. And indeed, our setting can be recasted as a resource theory. In this resource theory, the allowed operation is called restricted closed local operation and classical communication. And here RC LOCC means that the allowed operation is composed from the three basic operation steps. So first, I would say that in this scenario, we cannot add a pure state into it. Otherwise, because from a pure state, we can extract private randomness naturally. So if you allow the pure state for free, then the rate will tend to infinity. Then the local operation is local unitary. And in some setting, we allow local noise. That means the purifying subsystem is at the adversary side. Also, we may allow classical communication that is simulated by a diffusion channel from Alice to Bob. And the purifying part of the channel belongs to the adversary. Indeed, we can prove that in this picture, it is equivalent to the standard picture where a quantum system of two independent randomness is of this form. And in the standard picture, to extract randomness state, of course, pure state is not allowed for free. And but there, the strategy is to apply a unitary and then perform a standard measurement or part of the subsystem. And but here, if we don't consider the system for the adversary rho E, then we can just restrict it to the operation RC LOCC. And in this picture, the standard, the state of two independent randomness bit is of this form. Here, rho A K is arbitrary unitary, and rho A prime B prime is a fixed bipartite state. And in this state, it does not contain the state of rho E. And indeed, this is obtained by the purification of the standard state rho A, B, E, and then you twist out to the state of rho E, then you can obtain this form.
So sorry, I have a question. What is dual picture in this context?
We would call it a dual picture because in this picture, we need not to consider, or we need not to include the state of rho E. But in this picture, then we have to consider the state of rho E.
Yes, yes. Mm.
And before I explain the result, let's do a warm up. And indeed, it is a well-known protocol called entanglement swapping. From the slide, we already know that a local noise, that means the maximum mixed state, is useless by itself. But here, from the entanglement swapping, we can see that local noise indeed can help if it is used. It is used in combination with other states. So what is the entanglement swapping? It is a scenario like this. A1B is a Bell state, and A2E is another Bell state. And this Bell state is shared between Alice and Bob, and this one is shared between Alice and Eve. So if there is no A2, of course, if Alice, in Alice's eyes, A2 is max mixed, it is local noise. And if without A2, just with A1B, Alice cannot extract randomness larger than the dimension of A1 here, 2. So without A2, Alice can only extract randomness by 1 bit. But here, if he has A2, then perform a Bell measurement of A1 and A2. This is the standard protocol of entanglement swapping, and he obtains 2 bits. And indeed, from the entanglement swapping, we know that if Alice discloses the measurement outcome, then Bob and Eve can recover a fixed Bell state. The point here is that if Alice does not disclose the measurement outcome, then this value plays as the randomness. Because here, the reduced state of E is maximum mixed, remain invariant, and both state is still maximum mixed, invariant. And if Bob and Alice and Eve do not collaborate with each other, then they cannot learn the value of the Alice measurement outcome. So indeed, in the entanglement swapping, the measurement outcome plays as randomness. So here with the local noise, Alice can extract 2 randomness bit. Without the local noise, she can only extract 1 bit. So from this simple protocol, we can see that though local noise itself is useless, but it can help other states to extract randomness. Then
can I ask a question?
Mm-hmm.
But then do you have to discount this local noise from the final rate?
No, because as I said that local noise itself is not randomness, is not private randomness cannot be used to generate private randomness.
Or need not be private. It's local noise, but can be public.
Right, but here we consider private randomness.
Okay, thank you.
You're welcome. Then we turn to a more general case that I mean, the quantum state merging can be regarded as a general setting for the entanglement swapping. And then I explain it, and then we can see why we would employ the quantum state merging, or indeed we call it virtual quantum state merging as a main tool to obtain our results. The quantum state merging, and well, in the quantum state merging, indeed the E will the E part played as a reference, but in our setting we okay, let me just explain quantum state merging protocol first. A quantum state merging is a protocol saying that this is a pure bipartite state, and here the B system played as a reference system, in the sense that B does not any operation on his system, and A perform some operation on his system and send part of his system to E here, and then E performs some global operation with his initial system and the received part from A, and then the pure tripartite state file is recovered in this part between B and E. And of course, Alice it is not necessary for Alice to send all his parts to E. And the remaining part, A prime, is entangled with some part of Eve's system, E prime. So the goal is in quantum state merging is to consider the case, what is the minimal quantum system that should be transmitted from E from A to E, such that E can perform some operation to recover the tripartite state between B and E. Well, the answer is that, of course, there are different tripartite states, and in this tripartite state, where it satisfies the conditional entropy A given E is negative, then sorry, I should rephrase the quantum state merging in another way. Well, Alice is not allowed to send the quantum information. I mean, is not allowed to sending quantum state directly to Eve, but he can only transmit the quantum state by use of entangled state shared between A and E, and classical communication from A and E. Oh, sorry for that. I mean, Alice can perform a measurement of his system and obtain the result, and he then send the classical information. That means the outcome to E. And because initially A and E share some, can share some entangled state, then finally the tripartite pure state is recovered between B and E. I mean, before I said that, of course, this is another protocol, but this is not the protocol we will use. In the protocol, of course, if there is a quantum channel, you can directly send the quantum state through channel. A replacement for the quantum channel is that if you share some entangled state between A and E, and then use the quantum teleportation protocol, then Alice can send can just send the classical bit, such that the effect is to send
Sorry, I have a question.
quantum state.
I have a question. What is QST? Quantum science and technology? What is QST?
Okay. Oh, sorry. Well, this is the, I think, yes. Quantum state transfer. Transfer, yes. But here, I mean, quantum state transfer means that Alice can directly send the quantum state to Eve. But the original quantum state merging does not allow direct quantum transmission. Sorry about that. Okay. But anyway, they are equivalent. I mean, and from here, we can see that in this case, if the conditional entropy S given E is negative, then indeed the initial entangled state is not necessary, and after you perform this protocol, additional entangled state can be obtained. For example, for A prime, E prime. And if you look at this, A prime then plays as noise. I mean, of course, it cannot be used again to this original state because the original state is already destroyed. But local noise is created at Alice site, and the new local noise can be used for fresh copies of state. And from the last slide, we learned that local noise can help to extract private randomness. So quantum state merging can create local noise. But at the same time, if we look at the quantum state merging closely, then we can know that in this protocol, the classical communication that is needed is the randomness that Alice generated. The intuition here is that if Alice does not announce the classical communication, indeed the classical communication is just the measurement outcome of Alice measurement in the quantum state merging. If she does not announce or does not send the measurement outcome, then he does not know nothing about the measurement outcome. Otherwise, we need not to send. If he knows the measurement outcome, then we need not to send the classical communication in a quantum state merging. So in this sense, the quantum state merging say that the measurement outcome of Alice measurement is the randomness generated by Alice, and the randomness generated is private to Eve because he does not know the measurement outcome. Also, after that, the remaining part is local noise. So it's good to see that in the state merging protocol, indeed, Alice measurement had two effects. One is that he can generate private randomness. The other is that in this protocol, she can create local noise. And indeed, in our protocol, we will use this picture to obtain the main result. But here, we notice that in quantum state merging, indeed the required classical communication rate is the mutual information between A and B plus a negligible number of data. But this negligible part data would create correlation with Eve's system. So we have to delete the correlation by the technique of privacy amplification. But then we can get the rate of IAB minus data, a small number of data that is negligible. So the rate is not the rate does not change. And also, I would say that in the quantum state merging, because in the whole process, the B part remain invariant. So the randomness generated by here K is also private to B. So I mean, in this picture, the randomness here generated, or the K part is private to B and also to E. Still, there is a helpful part of local noise A prime. Then formally we obtain a doublet decoupling theorem that says something about that says something formally of the quantum state merging. This is a theorem given epsilon data to small number, and for n copies of pure tripartite state, when the number n is large, there exists a unitary or n copies of a system to K and A prime, and K will be used to generate the randomness part, and A prime plays as the shielding part. And under the operation of transformation of UA, then we can obtain such a state. And in the standard picture, if you perform measurement in the basis I or just all the K part, then we can obtain that the outcome I is almost decoupled from the state of B at the same time, it almost decoupled from the reduced state of E. Of course, this part, the I, are not decoupled from rho B E. I mean, they are correlated with BE, but they are not correlated with the individual part. And also we can obtain the rate, I mean, the dimension of the system of K. Its dimension is given by this formula. Here, this term is the mutual information between A and E. This is the mutual information between A and B. And the K part will be the randomness bits. And this term is used to for Alice to generate private randomness at Alice site. And then we can, I mean, interweave this theorem with Bob's extraction. And the idea is that for this part, we Alice perform extract randomness from just some part of this n copies. And after that, this p n copies, I mean, Alice used p n copies to extract randomness or Ka part. And then after that, because after that, this Pn part will shared between B and E. So in the eye of this eye, this part will act as a local noise. And
so I think it's time. And
I'm sorry.
Could you hurry or summarize?
Okay. I'm sorry for that because it. Okay, then we obtained the main result of the two-sided randomness extraction. It well, we have considered the 4 settings, and this is the region, and this is this one, and this is the picture for that, and well, this is the distributed data compression that given by the result is given by the Sapien-Wolf theorem. Also, well, we consider the one-sided randomness part setting, and we obtain some results. Here, I would say that we obtain the randomness that can be detailed from a Bell state. Also, well, this is dynamic setting when we consider a noisy channel, and the scenario is here is that Bob would like to extract private randomness, but he cannot prepare quantum state. Of course, there are some surrounding particles he can perform measurement, but potentially these quantum particles can be entangled with Eve. Luckily, there is a trusted quantum channel and connected with a trusted server A, and the server can prepare the quantum state and send the quantum state through channel to Bob, and then Bob can use this, receive the quantum state to generate randomness. This is the setting, and the task is that Bob would employ the quantum channel to generate private randomness as much as possible. Then the natural question is, what is the maximum rate? Of course, this is a channel capacity problem, right? And in this setting, we can obtain the complete answer for this. And it is given by this formula. And we notice that this term is just the reverse coherent information of a quantum channel. And it is has a single formula. And this term is long known, but its interpretation is unknown for a long time. And compared with coherent information, it is just difference is this the first term here. Okay, thank you. I'm sorry for not arranging time properly.
Thank you very much for your talk. So any questions?
I'm sorry for that because I focused on explain the picture why the protocol works.
So sorry. So could you explain again what is the private randomness capacity of channel? So could you show me the slide of that result?
Okay. Well, so here the task is that Alice should choose some proper input state to the quantum channel, and after receiving the state, Bob perform measurement to generate private randomness against to Eve, and indeed the randomness generated is also private to the sender Alice.
Yeah.
And then the capacity problem is that how could Alice choose optimal input such that Bob can generate maximal randomness per use of the channel?
So then what is the formula of the formula?
Okay, this is the formula. And why we can obtain this formula? And well, indeed, well, you can see that this part is okay. After use the channel, A, B, and E share a tripartite state, and then the task is reduced to having such a tripartite state. How could Bob generate randomness?
Sorry, I think this setting you need to make some assumption for the restriction for the Alice's measurement, Bob's measurement.
Sorry, could you repeat Bob's?
In this setting, so there is some assumption for the Bob's measurement. There is some restriction for the Bob's measurement.
Yes.
Bob
can only
make any measurement. Bob
no,
can any randomness, any amount of randomness.
True. That's true. I mean, Bob can only perform standard measurement. I mean, in the
Project measurement.
Yes, projected measurement.
Okay.
And of course, Bob cannot prepare any pure state. Otherwise, he can already generate private randomness himself. Yes.
Other questions? So thank you very much for your talk.
Oh, thanks.
Thank you very much.
Okay.
So then, don't you take a session here, next session?
Okay.
3 sessions. You will be take the role of session chair in the next 3 sessions.
Okay, no. Stop share. Hi, Baichu.
Hi, I'm here.
Hi, Baichu. Could you share your screen?
Okay. So can you see my screen?
Yes.
Oh, okay. So shall I begin now?
Okay, let me introduce you. Okay, this is the next talk given by Dr. Bai Chu Yu. He will talk on a brief introduction or information causality. Please.
Okay. Thank you, Professor Yang, and also thank Professor Hayashi to organize this meeting. In today's talk, I will make a brief introduction on information causality based on the references below. So we all know that the state space of quantum mechanics is a vector space. So, but it would be very interesting to find out what is the underlying principle of such postulates. And in last decades, it was understood that quantum entanglement plays a crucial role in addressing this question. So the most direct signature of entanglement are the quantum correlations obtained by measuring the subsystems separately. So the set of probability, to simply speaking, the quantum correlation is the set of probability distributions here, where x1, x2 are the inputs for different parties, and a1, a2 are their respective outputs. We know that the quantum correlation is larger than the set of quantum correlations is larger than the set of classical correlations. Here, the classical correlation means that those correlations that can be explained by the local hidden variable models. So, as an example, for the famous CHSH inequality, the boundary for classical correlation is 2, but the quantum correlation can reach 2 squared 2. So then our task, what we want to do is to recover quantum correlations with a physical principle. So more specifically, we want to bound the allowed set of quantum correlations by using some physical principles instead of applying to the form of quantum mechanics. So of course here the first such principles we can think about would be the non-signaling principle. Non-signaling principle means that is a principle stating that the distribution of local some local variables, so the local observables will not be affected by the measurement choice of the distant parties. So you can also see the equation here. So it's a general form of multipartite non-signaling principle. And it is known that non-signaling correlations can attain the boundary 4, that is more than 2 square 2 for the CHS inequality. So the non-signaling correlations form a larger set than the quantum correlations, and the quantum correlations form a larger set than the classical correlations. We can see in this picture, we show a slice from the polytope of the correlation space. The outer blue diamond is the non-signaling correlations, and the circle in the middle is the quantum correlation, and the one inside is the classical correlation. So we can see that there is a strict inclusive relation. also from this picture, we see that stronger principles are needed to recover quantum boundaries. We cannot recover the boundaries of quantum correlations just by using a non-signaling principle. Okay, so now we come to introducing the information causality as a physical principle. And this part is based on the original paper of the information causality by Pawlowski et al. And in a communication scenario assisted with non-signaling resources, the potential information obtainable will not exceed the information of the message sent. So more precisely, it will not exceed the channel capacity of this communication. So by this principle, we can place stronger boundaries for the resource used than non-signaling principle. So here I marked the phrase potential information because of course to understand information causality, we need more detailed understanding to this phrase. What is the potential information? So there are several explanations to it, but to me, I think there hasn't been a very strict and final answer to what the potential information is by now. So this is also the reason that lead to several open questions on this topic. So we will see this later. Okay, so in these slides, I will make a very brief introduction to the scenario of information causality in the simplest case. So in this picture, the system in the blue box is the non-signaling resource. So this protocol is device independent, meaning that the only thing we know about the system is that there are two distant parties, two local parties, Alice and Bob, and they can share a non-signaling resource. And that is all. We do not know more about the system. And what the resource can do is it takes in the local inputs. Here is X and Y, and they can output the respective output, the A and B. And in this simplest scenario, we have 3 random bits, A0, A1, and T. And so the A0, A1 belongs to the Alice side, and the T belongs to the Bob side. And we see by the following protocol. So the input Alice will do is that he will input the A0 O plus A1 into the resource. Here the O plus means the plus modulo 2. And Bob will input his the bit of random bit T here. And in the scenario, 1 bit of communication is allowed. Here it is denoted by M. So we see the way that Alice encode the message is she do it by A0 O plus the small a. The small a is the output of Alice side. Then after receiving the message of Alice and also the local output of Bob of his resource, Bob can give a final output. Here we denote it by the beta condition on T. So the final decoding that Bob do is he O plus the B and N, and by this protocol we can obtain we can calculate the information causality inequality I will say IC inequality in the following talk. So this is the IC inequality. It says that the mutual information between the Bob's output given the T0, given T is equal to 0, and the A0 plus the mutual information between the B condition on 1 and A1 would not exceed the K. Here K is the channel capacity. In this simple scenario, K would be smaller than 1. When the channel is perfect, then K would equal to 1. So in the original paper, it is proved that quantum correlation satisfied IC inequality. However, some non-signaling correlation violated. For example, we consider when the channel is perfect, if Alice and Bob share a PR box, so we know that PR box is a non-signaling correlation, but it's not belong to the quantum correlations. So when they share a PR box, we found that the first term would equal to 1, and the second term would also equal to 1. So this means that when Bob inputs 0, then he can extract he know exactly what the bit A0 is. When he inputs 1, he know exactly what the bit A1 is. So we can feel something strange here, because Alice just sent 1 bit. Although Bob cannot extract the information of the 2 bits A0 and A1 in one round, but he has potential to obtain the information of both these bits. So in this case, we see that the IC inequality would be violated. Okay, so now I'll introduce some important point in the proof that quantum mechanics will satisfy IC. So this is not a detailed proof, but I just take out the important point. The first important point is that we must show that every term, the AI, the mutual information between AI and B given I, would be smaller than the one on the right. So here the row BM is the Bob's Bob's local system after he received the communication bit M. So it is the joint system of his local system and the bit of communication. Okay, so this can be proved by using data processing inequality. So this is a form of data processing inequality, and it is shown that the quantum mechanics satisfies the data processing inequality. So here the B is the original system. B prime is the system after Bob makes some local quantum operations to his local system. Okay, and this is the first point. And the second point is that we must show that the sum of the left side would be smaller than the term in the middle. And here the variable A is the joint variable of A0 and A1, because we can see that although A0 and A1 is independent, but they can be written as a joint variable. Okay. Okay, so the next is that we see that the protocol of information causality is theory independent. It means that we do not rely on knowing the details of the theory to use this principle. So a natural question would be, what properties would a more general probabilistic theory need to have so that it would satisfy information causality. So there are several works that solve this problem. I try to answer this problem in different perspectives. So now I just choose one of them that I think is easiest, simplest to understand. So it says a general probabilistic model must satisfy the following conditions. Oh, so before I introduce it, I must remind that so for a specific general probabilistic theory, the definition of entropy, there would be a specific definition of entropy. So all the following condition is place a constraint on the properties of the measurement entropy measure. I'm sorry, place a constraint on the entropy measure. The first one is data processing inequality. So consider two systems A and B. The DPI is that for any allowed state and for any allowed local transformation, we must have the following inequality. And the second is that however the conditional entropy is might be defined, the all allowed state on AB must satisfy the following. It seems very natural. And the third one is that the entropy measure must reduce to the Shannon entropy if the system is classical. So this part tells us that if you want to study whether a given general probabilistic theory satisfies IC, we should know the exact form or at least some properties of its entropy measure. Okay. So after these experience,
sorry, can I ask you a question? Sorry
of course.
to interrupt you. Can you go to the slide before? I mean, the second condition seems to be extremely strong, right? Like even if any entropies do not satisfy A2. I mean, that is a special, I mean, conditioning is an averaging, right? And that's a kind of property of Shannon entropy. So like.
Oh, okay. So do you think that the definition 6 is very strong?
Yes, I think so.
Okay.
Anyway, I don't know. Sorry to interrupt you.
Oh, okay. No problem. Oh, okay. Maybe we can talk about this later. Because for me, it seems that it's more like likely more close to a definition, but but maybe we can talk this later. Okay, so after this literature, I think maybe there's I have a possible explanation for the potential information. So that it is the mutual information between the A and the BM. Here, BM is just the joint system of Bob and the communication bit and the communication message. So the role of IC protocol is to obtain a value that is close but does not exceed this value. Now I introduce some open question an open question of this topic is that does IC principle recover all boundary of the quantum correlations? And especially particularly we want to know that if IC principle can rule out the almost quantum correlations. So I will not make a detailed introduction to it by now. But why is it important? Because many other principles to study the boundary of quantum correlation are proved they cannot separate almost quantum correlation and the quantum correlation, but it is not known by now whether information causality can do it. So in the following, I'll show some slices. The first, in this slice, the almost quantum correlation, and IC correlations coincide. But there are also slices that, in this slice, almost quantum correlation and quantum correlation coincide. But we see that the IC correlations form a larger set, so it's not strict enough. And also, there are slices that, for example, in this slice, so the almost quantum correlation set is slightly larger than the quantum correlation set. So we cannot see it here, but maybe you can see the red line. That is, this red line is the quantum correlation, and the almost quantum correlation is very, very close to the red line. We cannot see the difference here, but there is a gap between them. And also we see that the IC correlation also form a larger set than the other two. So I think this is okay. So according to some recent study I made, I found that some of these gaps may come from that the protocol or inequality of the present IC protocol is not optimal. So by now, the optimal protocol of an inequality to extract the potential information is not known. So, so now we are working to improve the IC boundary in the former slices by modifying the form of IC inequality. So, but it is we have not completely finished, so I will not show it here. Okay, so I think that's all of my today's talk. Thank you.
Okay, thanks, Bai-Chu, for the talk, and questions or comments.
Sorry, I have a question.
Okay.
On your abstract, you mentioned the relation between information causality and Markovity. Could you simply explain the relation?
Oh, okay. So at first, I need to say sorry about my talk today is not the same as the one I give before. The reason is that first, the time of my talk has changed. The second and more important reason is that I found that recently that the Markovity is not the relation between the Markovity and the IC is not so strong. So in the classical case, so I think the one we really need. I'm sorry, how to go back. I'm sorry. Can you see this slide? The property that we really need it seems to be the data processing inequality. But in the classical case, the Markovity implies data processing inequality. And but the situation is different in the quantum case. So in general, it does not. So in the quantum Markovity can imply data processing inequality, but it is not the general case. So it is a little complicated now for here because I did not put the definition of quantum Markovity here. So the definition of quantum Markovity, for example, it contains three systems. So A, B, C, and B is the mid-intermediate system. And the condition that this system form a quantum Markov chain is that the joint state rho ABC can be obtained by joint state rho AB by operating some local operation on B and a shear like C. And this is the quantum Markovity. But we can see that how to say the form of the data processing inequality is more general than the quantum Markovity, because we can consider the quantum measurement case. So in the quantum measurement case, the intermediate system B will not preserve. So it will change in the measurement process. So it is better just to consider the data processing inequality instead of consider the quantum Markovity. So that is why I removed the part of Markovity in my talk. So I'm sorry, maybe it's a little complicated, but is it clear to you?
Okay, you mentioned that in order to investigate the relation between the information causality and the Markovity, you should something extend the sum of setting or and so on. Is it correct?
I'm sorry, I didn't hear you clearly. Can you repeat?
In order to investigate the relation, we should extend some of setting of so in this talk, information causality is considered in bipartite case, but you mentioned that quantum Markovity is essentially the third party case, right?
I think not exactly, but because we can treat the BC system together as a local system. It does not need to be a tripartite case, but the main problem is that the quantum Markovity requires that the intermediate system B is unchanged during the process. But but it's not general enough, because for example, when we make quantum measurement, so although the quantum measurement can also be written as a unitary in the larger space, but it will change the system B, so it cannot be explained by the quantum Markovity, but it does lead to a form of data processing inequality.
Okay, I see. Thank you.
Okay, thank you.
Any other questions? If not, let's thank the speaker again.
Thank you.
Thank you.
Thank you.
So maybe next speaker can prepare his slide.
Yes. Sorry, I cannot hear you.
Can you hear?
Yes, yes.
I can hear, yes. Okay, so could you tell me how I can pronounce your name?
It's Aditya.
Okay.
Yes.
So now you can share your screen.
Yes. Just a moment. Yeah, just give me a moment. I'll just share my screen.
Hmm? Your screen does not work?
Yeah, it's somehow not allowing me the access to share Mac.
Eh?
Yeah. Give me a moment. I'll log in from a different ID. Yeah, I'm really sorry for the delay.
But there is no restriction. Of course, the previous speaker should close sharing. So once previous speaker close the sharing, then this is okay. Now by to close is sharing, I think.
Yes, I have already closed my share.
Can you try? Can you try sharing again? Still impossible. Okay.
He's not here.
He's not here now.
退出しちゃって。
He said that he will log in with another device.
Another device. Okay, I understand. Another device. どうした TCP.
Hello, am I audible?
Okay. Please,
Yes.
Hello.
Yes.
Hello. Yes.
Yeah. Really sorry about the delay. I'll just share my screen.
So Aditya, do you want to share the slides on the chat and then someone else shares the slide and you talk on top of them? Aditya, did you hear me? Do you want to share your slides on the chat? And
Yeah.
then someone else can share them and you can talk on top of them.
Yes. Yeah, I'll just do that. Yeah, I don't know why I'm unable to access.
Yeah, we don't know either.
So is it okay if I email it to you? Maybe you can
just share it on the chat.
Okay.
So everyone can have it.
Yeah.
I hope it's a PDF.
Yes.
Very good.
It's there on the chat.
I think Francesco handling that sharing, screen sharing, because you are co-author, collaborator, so you are most suitable. So
Okay.
other guy could not understand how to handle.
Yeah, I'm really sorry about this glitch. Yeah.
Mietemaska?
Okay. Thank you very much.
Okay, shall we start now?
Yeah.
Yes, please start.
Okay. The next speaker is Aditya Nema. He will talk on one-shot multi-party purification distillation. Please.
Okay. Good morning, everyone. I'm very sorry for the technical glitch, first of all. So I'll be talking about one-shot multi-party purity distillation. This is still work in progress. So I'll present the parts like for which we have proof and which we shall submit to archive shortly. So this is joint work with Santan Chakrabarti, who is a postdoc at CQT in US, and with Francesco Buscemi, who is currently my supervisor at Nagoya University. Next slide. Yes, so we'll start with a very high-level description of the problem. So suppose there is a mixed quantum state, rho A. So it's a density matrix where we can assume that the system A is with Alice, or the Alice possesses state rho A. Now the task is to be able to distill as much pure states as possible from this rho A by application of only local unitaries. So this problem was first posed by Devitak in 2004 in this particular language. Now, earlier, it has a rich history, but we'll restrict ourselves to the setting that was described by Devitak in 2004. Now, there was a generalization, which was again given by Devitak in the same paper, which concerns two parties. So we have a mixed state rho AB, where the part A is with Alice and the part B of the state rho AB is with Bob. Now, the task is again, can they both do some operations on their respective halves, which are A and B, and distill some amount of pure states by using only local purities and maybe some other resources, which we shall see shortly. Similarly, we asked for a multi-party generalization for the above problem. So note that Devitak has done this problem in the asymptotic IID setting, where we have access to n identical copies of rho A and we let n go to infinity. And then we give up, and then Deptech gave a particular rate region for this, which we shall see what the rate region is. Next slide. Okay, so this is the detailed description of the problem. So we'll start off with a single party case where we have a state rho A with Ls, and A is like mod A dimensional, and rho A is an operator on mod A dimensional Hilbert space. So it's a density matrix. So when we say we want to distill purity, all we mean is we want to extract pure state specifically of form Ket0 Bra0. Now, if the state on rho is of dimension A, we can distill purity, let's say up till dimension AP, and AP is less than equal to A. Now, we'll give a trivial check that if mod AP is equal to A, then there's nothing to distill as rho is already in pure state of form Ket0 Bra0. Now, if rho A were to be maximally mixed state, which is a form identity by A, then intuitively we think that we cannot do anything. Like there's no way we can distill pure states out of this, as each and every eigenvalue is same with the magnitude of 1 over the dimension of A. Okay, so we shall see what can be done in between when these trivial cases are not there. Now, the next thing is, what are the allowed operations by Ls? As we mentioned earlier, Ls is only allowed to do a local unitary on its state. And if she decides to borrow some ancilla, she has to do it catalytically. So catalytically means Alice should promise that she'll return the ancilla at the end of the protocol. Okay. Now, just a small note about what pure state is. So why we are saying Ket0 is the pure state? Because we are allowing local unitary operations for free. So if we can create a pure state from a given state, then we can apply another local unitary on the state to go to any other desired state. So we'll restrict ourselves to distilling the state of form Ket0. Okay. And in multi-party case, we shall allow unidirectional classical communication from Alice to Bob. So specifically in the bidirectional case, and the reason we'll see shortly. Next slide. Okay, so this is the protocol for the single party case. So this is the newer version of the protocol, which was given by Deptech. So as I mentioned earlier, Deptech did it in asymptotic IID setting. We give a one-shot version of it. So let's see. So the aim is to be able to distill as much pure state as possible from a given state rho A. So let's say the dimension of pure states that we are distilling is AP. So the qubits that we'll be distilling of form Ket0 is log of mod AP. So we want a theorem something like this. So we want to find the maximum value of this log of mod AP such that there exists a unitary which acts on this rho A, and the resultant state is close to the pure state, which is Ket0 on dimensional AP, tensor some other state on the rest of the Hilbert space, which is of dimension A by AP. And we define rate as the maximum value of log of mod of AP. Okay, so the theorem says, so intuitively, what is the rate? So intuitively, what we think is that we will look at the, so first of all, we'll look at the spectral decomposition or the eigen decomposition of rho A. We'll arrange the eigenvalues in ascending order. Then we'll look at all the eigenvalues that sum up to at most epsilon. Let's say we zero them out to go from rho to a matrix rho A, rho prime A. So again, rho prime A is nothing, but it is a matrix which is obtained from rho A by zeroing out the smallest eigenvalues of rho that sum up to at most epsilon. Okay. So
sorry, I have a question. So I missed the what is the goal of your protocol? What is the goal?
Yes, the goal is given a state rho A, come up with some unitary such that this state u rho A u dagger is epsilon close in one norm to the state of form Ket0 Bra0 AP tensor some other state on dimension A by AP. So we have to distill, we have to find out how much Ket0 Bra0 we can distill from state rho A by application of only unitaries.
So using unitary,
Yes.
what kind of state you want to make? You make AP and AP slash AP.
This is A upon AP. Sorry. This is A divided by AP. So this is the rest of the Hilbert space. So I want to distill pure states of form Ket0 Bra0. And I'm saying that I can distill log of mod of AP number of states of form Ket0 Bra0 from state rho A by applying a unitary U.
Now you want to make vacuum state, state 0 in system AP.
Right.
And another system, rho prime. Rho prime is some kind of junk system.
Yes. Yeah. So for the purpose of this talk, this rho prime will be a junk system. So this is where the maximum information of rho A lies. but we are not aiming to find out what is the information that is there in row A, but we are trying to find out how much redundancy is there in row A so that we can fit in pure state of form Ket0 Bra0 there.
Oh.
Yeah, so like usually we would say that we want to come up with a matrix rho prime which is close in one norm to rho. So in other words, like if we look from a classical point of view, given a distribution, I want to shape it so as to match some other distribution. But here the goal is in some sense dual to it. So I want to see the redundancy in a distribution and fit in zeros in those redundancy places. So is this clear? So the purpose is that, okay, so when I apply this unitary U on rho, and if I trace out a suitable dimension subsystem, the resultant traced out state should be close to the state Ket0 Bra0. That's the goal. And to find out what is the maximum dimension of the state Ket0 Bra0 that can be extracted.
Please proceed. So.
Okay. Yeah, thank you. So then we define an entropic quantity, which is a variant of the max entropy. So we call it as H tilde epsilon max of A evaluated with respect to rho. So this is nothing but log of support of the state rho prime, where rho prime is the state that is obtained from rho by zeroing out the smallest eigenvalues that sum up to at most epsilon. And we can also show that this new entropic quantity converges to the Shannon entropy or the von Neumann entropy in the asymptotic IID case. So the theorem is that the number of pure qubits that I can extract or I can distill from the state rho A by application of a unitary is log dimension of A minus the entropy, the max entropy content of rho, this modified max entropy content of rho. Okay, next slide. So we'll just see a quick proof sketch of this. So the proof is like, in this case, very intuitive. So what should be the system AP and what should be the system AQ, such that AP tensor AQ is isomorphic or is equal to the system A. Okay, so for the purpose of this talk, I won't be very technical. So we can treat this isomorphism as equal to. Okay, so as we mentioned earlier, that if we look at the definition of this H max tilde epsilon of A, then we have a subspace AQ, which is of dimension 2 to the H max tilde epsilon of A. And if I define a projector onto this subspace AQ, then I know that trace of this projector is nothing but AQ by the definition of this projector. And when this projector hits on the original state rho, this is at least 1 minus epsilon by the definition of this pi and the system AQ. Further note that all we have done is we have just zeroed out some eigenvalues and just thrown away those eigenvectors, retained everything as it is. So pi and rho commute. This means that AQ is isomorphic to the eigenspace of pi rho pi. Okay, so let the eigenvectors of pi rho pi be AQ. Now they also belong to a basis vector of AQ. Now further, let I prime on A be the eigenvectors of rho A. Now since pi and rho commute, we know that there exists an embedding from the span of AQ to the span of A. That is, I can come up with an isometry or a unitary. So I can come up with a unitary matrix that maps the basis of AQ or embeds the basis of AQ into the basis of A. So this is just relabeling the vectors, the eigenvectors of the system A. Okay, next slide. So this is the following embedding. So what we do is, so we know, so let's say rho I prime is an eigenvector of rho. I apply a unitary U and map it to Ket IQ tensor Ket0. So this can always be done such that when I apply this U on pi rho pi, this is equal to pi rho pi on AQ. Now this is on AQ dimensional system, tensor Ket0 Bra0 on AP. So this always I can do. So now we know that since rho and pi rho pi are close by the definition of pi, this is at most epsilon. And since one norm is invariant under the application of unitaries, so if I apply from the above state U on pi rho pi from the above equation, this is very close to pi rho pi on the system AQ, tensor Ket0 Bra0 on AP. So this is less than equal to 2 root epsilon. So this can be shown by gentle operator lemma or just by going through the definition of these pi, rho and u's. So how much purity we've been able to distill with this log of dimension of AP, which is just mod A by mod AQ. So ultimately we've been able to distill log A minus H max tilde of A. So this was the proof. Now, if we look at the asymptotic IID setting, all we'll do is take this row to the tensor power n and apply limit as n goes to infinity, then limit as epsilon goes to 0. And we'll get the rate as log of mod a minus HA of rho. So DefTech showed this along with the matching combination. And notice that even in our case, which is the one-shot case and the asymptotic IID case, if rho is a maximally mixed state, then the amount of purity that can be distilled is 0. So this even justifies the induction. Okay, next slide. Okay, now we look at the bipartite case where we are given a mixed state rho AB. Alice is given a system A of this rho A. Bob is given the part B of this state rho AB. Okay, and the goal is for both Alice and Bob to jointly distill maximum amount of purity from their respective halves. Okay, so one straightforward way can be that let Alice apply the knife protocol on her part, the local protocol on her part, Bob apply the local protocol on his part. So if Alice applies the local protocol on her part, she'll be able to distill log mod A minus H max tilde epsilon of A amount of purity. Similarly, Bob will be able to distill plus log B minus H max epsilon tilde of B. So notice that there are no discrepancies here because Alice is applying a local unitary, which won't disturb the state at Bob's end. Similarly, Bob will apply a local unitary, which won't disturb the state on Alice's end. So naively, this can be an achievable rate. Okay. So now we ask the question, can classical correlations help to increase the rate? So let's take a look at a simple example. So suppose we have a classically correlated state, which is given by ket0 bra0 on A, tensor ket0 bra0 on B by 2 plus ket1 bra1 on A and ket1 bra1 on B by 2. So if we compute these entropic quantities, they'll turn out to be 1. We have taken A and B to be two-dimensional system. So this overall rate turns out to be 0 in this case, when even we have a classically correlated state. Can we do better? So suppose we are allowed classical communication. Then if Alice just sends her system through a noiseless classical channel to Bob, so Alice won't distill anything. And then if Bob applies a C0 gate on his part, controlled on what she received from Alice. So the controlling bit will be what Bob received from Alice, and the NOT gate would act on Bob's state B. Then we know that, so the C0 will be a form ket0 bra0 tensor identity. Note Bob can do this because Alice has transmitted her share to Bob. And this one part controlled on this one would be turned to 0 by the application of a NOT. So this tells us that Bob can indeed distill 1 bit of purity. Okay, so naively, we would say that the rate is 0. But if we allow classical communication and there is a way to use correlations, then we can increase the amount of purity that can be distilled. Okay, next slide. Now we want to make this thing general. So before that, in the asymptotic IID rate, what is the extra amount of purity that can be distilled other than applying the knife protocol? So the extra amount of purity was the regularized version of the mutual information between X and B. Now X is obtained by measuring the register A by Alice. So we have to modify the rules that we mentioned earlier. So Alice and Bob again will be given access to local unitaries, but now Alice can use Ancilla in a catalytic way, and Alice can also perform a measurement and send classical communication. Okay, so this is the modified scenario. Now let's see the step-by-step proof. So as we have said that Alice can purchase Ancilla, Alice can borrow Ancilla catalytically with a promise that she'll return it at the end of the protocol. Okay, and Alice can also perform a measurement. So Alice applies a normalized rank 1 POVM, a lambda A, which is of this form, ket psi x bra x. So normalized, this means that the L2 norm of this vector psi x is 1, and it's a valid POVM, means if I sum over all the x's of these POVMs, it will turn out to be identity. Okay, so Alice do this coherently by borrowing log mod x amount of Ancilla. So the measurement result on the state rho A will give us a system X, and the probabilities will be denoted by Px. Okay, so Alice does this measurement coherently, meaning that she'll borrow this Ancilla in pure state ket0, apply ket rho, and after the measurement, the resultant state would be of form ket x on x, which is the measurement outcome, a pure state on A, because we are applying rank 1 POVMs, times some state on RB. So this is the resultant state that we get. Now this clearly tells us that Alice can apply a controlled unitary controlled on X and map all these psi x's to zeros, distilling purity, the entire purity of log dimension A from the state ket psi x. So Alice does apply this kind of a controlled unitary which maps psi x to 0 and distills log of mod A minus log of mod x amount of purity. So this log of mod x is the catalyst that Alice is returning now. And the resultant state is of form sigma x, ket x, psi x. So this will be turned to 0. So it's just ket x and phi tilde x on RB. Okay. Now, before moving on, I'll just like to remark that if we just look at the state, which is before Alice has applied the distillation, and that is before Alice has applied the control unitary, if I compute Ix RB, which comes from above here, this is exactly equal to H of A. Okay, so this is just a remark to keep in mind. This we'll see later. Okay, now in step 3, what Alice does? So after distilling purity from A, Alice is left with summation x, ket x, phi tilde x. Alice applies a von Neumann measurement on this in ket x bra x basis to obtain this CQ state of form sigma x pxx ket x bra x tensor rho xp. Okay, so again, notice that the state on Bob is unaltered. No operation has been performed on Bob. Everything has been going on locally from Alice's side. Okay, next slide. Okay, so now further from now the resultant state is tau xb, where x is with Alice, b is with Bob. So Alice can further apply the local protocol on the classical system ket x, or I can say that on the distribution px, and distill log mod x minus h tilde epsilon max of x amount of pure bits. Okay. And the overall rate that Alice now has is log a minus log mod x. This was from step 2. Then from this step, Alice can further distill log mod x minus h tilde epsilon max of x. So this gives us a total rate of log mod a minus h tilde epsilon max of x. So this is the rate that Alice has been able to distill on the whole. Okay, and the resultant state is the state that has been obtained after applying the unitary to distill purity from X. So which is the system X1. Then, so the state is of the following form. So since we have fit in zeros in the redundancy of PXs, let's say S is the high probability set in the under the distribution PX. So the resultant state of sigma X1B, where in the X2 we have distilled ket 0 bra 0, which is with Alice now, this is equal to summation over all x in x, pxx, because this is not modified at all, ket x bra x on x1, tensor rho x on b, and the appropriate normalization. Okay, and this pi is nothing but projector on S, which is just a normalization factor. Okay, now what can Alice do to be so that she can enable Bob to distill something more than just the what local protocol would give? So Alice wants some way that Bob should also be able to utilize correlations. So far, Alice has utilized correlations by the help of measurements. But we are not allowing Bob to borrow any further NSLR. But Alice should be able to guide Bob in such a way that Bob is also able to utilize something from this X1. Okay, so Bob will work with his local state rho b, and Bob will indeed distill log mod b minus h max tilde of b amount of pure bits. But we want Bob should be able to distill something more, which should come from what Alice can transmit to Bob classical. So naively, this won't work. So now what we do is, so given this control state, we want to apply the protocol of classical data compression with quantum side information. Since the state on Bob is dependent on the classical outcome that Alice has been able to create. Okay, next slide. Okay, so for this, we use a one-shot version of the classical data compression with quantum side information. So this was proven recently by one of the co-authors of this book. So given the control state, so first of all, we'll come up with a bijection, which maps the classical register X to some indices M and N. So this M, so this can be thought of as binning for the random variable X, and the bin number will be denoted by the index M, and the number of sequences in a bin, they are denoted by N. So is this thing clear? So all I'm trying to do is I'm just trying to represent X in a two-dimensional array, where the row is, where the columns are indexed by M and the rows are indexed by N. Okay. And the theorem says that for any epsilon given greater than 0, the maximum value of log n is at most the hypothesis testing relative entropy between X and B. And further, when we apply a bijection on X to map this X into Mn, we get some distribution on Mn, and the resultant state would depend on this Mn. Okay, so this we have to do in order to be able to utilize Bob's quantum state as side information in order to correctly decode X1. Okay, So for this, what do we need? We need a POVM because we should be able to decode X1, which is a classical state, from rho. So the final theorem says that under this distribution PMN, the average of rho MNB minus this measurement that is applied on rho MNB is closed. That is, the measurement has not perturbed the state on Bob too much, along with the fact that we have been able to recover X1 that L is transmitted using the quantum side information rho B. So it performs these two tasks for us. And the proof, like it's, as I mentioned earlier, is a binning strategy for X. So what to do? So bin X into M number of bins. Size of each bin is N. Now, in order to decode the correct X from a particular bin, which is transmitted, so apply one-shot packing lemma to it to get the rate in terms of hypothesis testing relative entropy. Okay, so for now, I'll just give, so I've just given an intuitive picture of this, but it's still a little bit more.
Sorry, I have a question.
Yes.
So you consider classical data compression with quantum side information, but in that case,
Yes.
why you have M and N? Usually only one practical system for compression. Why you consider two systems?
Okay. So that is because, so I'm performing random binning in order to obtain the compression.
Random binning?
Yeah. So a binning kind of argument. So the thing is that, yeah, I understand what you mean. So how do I utilize this side information? So what I'll do is, so I have all the outcomes X's. So suppose I bin them randomly and I choose the number of bins, which is equal to 2 to the H max. Okay. Then given a sequence X, I'll look at a particular bin in which that X was placed. I'll transmit that bin index. Now Bob's goal is to look into that particular bin and come up with the correct X that Alice wanted to transmit using the state rho XB. So I think what you are thinking is along the lines of measurement compression where there is shared randomness. So when that shared randomness is there, this M has just no role as such.
Which one is shared randomness?
No. So here there is no shared randomness so far. So here the goal is to be able to transmit X so that Bob can utilize his.
So there is no constraint for size of M?
Yeah, the size of M is 2 to the H max tilde minus this IH epsilon XB. This is the, so M is.
I can say that this is different from standard formulation of classical data compression with quantum size information.
Yeah, this is a slight variant.
Usually compression rate is given as conditional entropy. But why you have mutual information? Usually that compression rate conditional entropy.
Correct. I understand.
HX slash B.
Yes. So that is, So
why mutual information?
Yes, I am coming to that. So the rate that you're talking about, which is the conditional entropy, it is the rate of classical communication, right? So that much amount of bits you need to convey to Bob so that Bob should be able to recover X correctly. Now, in this case, the rate is still the conditional entropy, but it is given by H max minus this IH epsilon. So this is not the classical communication rate. So Alice is not transmitting these many number of bits.
But at least that naming is not suitable because
I see.
Classical data compression with quantum side information means that only the data compression for classical system. So then, of course, decoder can use the quantum system, side quantum system. So in that case, compression rate simply give us the conditional entropy. B. So you consider different problem. So you need to use different terminology and you need to more carefully explain what is your task.
Okay. No, that I see, but this is exactly the same task. So I want to compress.
Why compression rate is different?
Yes. So the compression rate the compression rate is the amount of classical bits that Alice needs to transmit to Bob, right?
So this kind of conditional entropy.
Yes. So that conditional entropy can be viewed as, so let's say we work in classical and asymptotic IID setting.
Yes, but why you consider mutual information? This is different quantity.
No. So the rate is given by hx minus I of xy, which will be h of x given y. Right? So that is what I'm trying to do. So the rate of classical communication, which is the compression rate when y is the side information, is hx minus mutual information between x and y. This will be equal to the conditional entropy, which is h of x given y. So I'm giving an alternate protocol to do this, which is, let's say you first compress x to hx number of bits or hx number of bins.
That kind of explanation is not so understandable for me. You need to write down something. So
Okay. Yeah, I understand. Okay, yeah, I'll change this.
but we don't have enough time.
Yes.
But this is
and
another
more than
thing.
20 minutes.
This is a different thing. This is a lemma of a different paper. It's the name.
Yeah.
So maybe.
So in the paper they give the same name. Yeah.
Anyway, we don't need to finish your talk. So because already more than 20 minutes. Passed.
Okay. Yes. I'm really sorry. I'll just sum it up. Okay. Next slide. Yeah. Okay. So this is the final result. So we've been able to show that if we apply a particular kind of theorem, which is in some sense a modification to, as Professor Hayashi mentioned, classical data compression, then the amount of the extra amount of information that we are able to distill, the extra amount of purity that we are able to distill is governed by this quantity IH epsilon between X and B. So the overall rate is log mod A minus H tilde. So this will be H tilde epsilon max of X plus IH epsilon naught of X semicolon B plus log B minus H tilde epsilon max of B. Okay, next slide. Next slide. Okay, so we can recover the asymptotic IID rates from this. Then, so by adapting this new kind of thing, which was analogous to the classical data compression with quantum side information, not exactly that, we've been able to save on the random bits. And this is what the slide mentions. And also we have been able to reduce the amount of catalytic ancilla than the conventional case. Okay, next slide. Yeah, okay. So now we consider the generalization of this problem, and we hope that we'll be able to achieve this rate, which is log mod A minus I max epsilon between X, Y, and BC. So this will come by the measurement compression or the classical data compression kind of thing. Then this is what Bob will achieve locally. Plus this is what Bob will be able to achieve from the correlations between Alice and Bob. Plus this is what Charlie will be able to achieve locally, and this with correlations from Alice and Charlie. Okay, next slide. Okay, so this is the conclusion. So the third three-party case is a generalized one. And yeah, so we have not still put up this work on archive. So we are still going through the final checks on it. And in future, we'll hope to do a multi-party case and see if we can relate in some sense this particular protocol to the so-called Grunwald information. So that is how we started off this work. Okay, thank you very much. And I'm very sorry for the delay.
Okay, thanks, speaker again. And any questions or comments? So I have one. Could you show the last slides? So could you explain the Grunwald information gain?
Okay. So suppose I have a state rho A, and I look at a purification of this rho RA, and I want to apply a quantum instrument on this pure state. So the quantum instrument will consist of measurement operators, which are indexed with this lambda sub x, and the result will be stored in the classical register X. So the resultant state after applying this instrument is the sigma RXP. So Grunwald information is defined as h of r evaluated over the sigma minus h of b given x. So it is the difference of these two entropic quantities. And we cannot say that this is some mutual information kind of quantity. So what we are aiming for is, can we use some version or some variant of the protocol that I just mentioned and say that the rate is in some sense equal to the Grunwald information in that case. So then that protocol might serve as an operational meaning to the Grunwald information.
Wait a moment. Each minus. Okay, thank you. Any other questions? Okay, if no, please thanks the speaker again. Thank you.